Today, we delve into the fascinating world of digital system design, simulation, implementation, and testing. Our presentation by Group 3, composed of myself, Richard Sarametta, Maria, Johnny, Ethan, and Miguel. We will go over the presentation and insightful exploration of the automated tools driving this technological landscape we find ourselves in today. Digital programming devices, also known as programmable logic devices. They are circuits that are programmed by the users to perform a certain task, generally faster and more efficient than fixed logic devices, last longer as well, and make up the building blocks of all things we use today in our modern electronic world.
Read-only memory, or ROM, are digital programmable devices that store data as binary. They consist of interconnected semiconductor arrays, and they store binary data that can be read but require specific operating conditions to change said data. They use truth tables to visualize the data, and the output of a ROM is known as a word. The size of commercial ROMs can range from 32 words by 4 bits to 512K words to 8 bits, or some of them even being larger. The internal of a ROM can be seen as a decoder and a memory array. Different types of ROMs exist, like programmable ROMs, which store data in electrical charges and can be used permanently until erased. Once erased, the data can now be stored in what's known as a EEPROM. EEPROMs are electrically erasable programmable ROMs. These are similar to PROMs, but they can be rewritten over 100 to thousands of times. And they can also be used at the time of manufacture due to the rewritable data it has. Programmable logic arrays, or PLAs, are similar to ROMs in functionality, but differ in the internals. They use the AND and OR gates instead of a decoder and memory array, and do not use truth tables like the ROMs. Instead, they use the sum of products expression. They have its own table known as a PLA table, which you can use to see the inputs of zeros and ones, if the input is complemented or not, the product terms of each output. A PROM or PLA can be used depending on the quantity of inputs required. PROMs are usually used for smaller numbers, while PLAs are better for larger quantities. Field programmable logic arrays, or FPLAs, also use electronic charges similar to the PROMs.
CPLD, complex programmable devices, are complex programmable logic device and completely programmable and/or arrays and macrocells. Macrocells are the main building blocks of CPLD, which contain complex logic operation and logic for implementing disjunctive normal form of expressions. When it comes to CPLDs, they are compared to PLAs and are easy to manage and make changes to. And also, when it comes to these, are non-volatile and easy to use, and having multiple benefits like advanced programming and low cost.
The FPGA design process begins with stage 1, the initial design entry. This is where you understand what the project needs and how it should work. You would draw diagrams or descriptions to plan out how everything will fit together and break the project into smaller parts to make it easier to work on. The next stage is the register transfer level design, or RTL design for short. The RTL design is a way to define the functionality and behavior of a digital circuit using a hardware description language like Verilog or VHDL. It lays out the detailed instructions for how the digital circuit will operate, like writing a detailed plan or blueprint for a digital design, explaining how each piece of the design should behave and work together. You also want to make sure each part can talk to the others correctly, and create tests to make sure everything works as expected during this stage. The next stage is simulation and verification, testing and making sure that the project will work as it should. Here, test benches are used to simulate the design and verify its functionality. Test benches are like virtual environments where one can simulate how the design behaves under different conditions. This is also where you would fix any other problems found during the testing. The following stage is synthesis, where you would convert the design code into a gate-level netlist that the FPGA can understand using specialized tools, such as Synopsys Design Compiler. This means each component of the design, such as the logic gates, the AND, or not gates, Flip-flops and other digital elements are represented by its corresponding gate level description. These descriptions map the logical operations to physical hardware resources within the FPGA and instruct the FPGA on how to create the physical circuits needed to execute the design. Also, during this stage, it is important to check and make sure the project uses the computer's resources efficiently. The next stage is implementation, where you're putting it all together. During implementation, algorithms are used to determine the physical placement of logic elements and interconnections on the FPGA chip. You'll connect all the parts together according to the plan, and then the synthesized netlist is translated into a configuration bitstream that can be loaded onto the FPGA device. The bitstream essentially serves as a blueprint for the FPGA, guiding it and configuring its internal resources to behave according to the specified design. The next stage is testing and debugging. This is where you'll be checking the project to make sure it does what it's supposed to and fixing any mistakes or problems found during testing. Debugging tools such as ChipScope or Integrated Logic Analyzer are used. The final stage involves deploying the FPGA design into the intended environment, whether as a standalone device or as part of a larger system. The FPGA is integrated into the overall system architecture, ensuring it fits perfectly and works correctly with the surrounding components. Then the system-level functionality and performance are verified to confirm that everything is working together as it should. Once everything is double-checked, the final product can finally be deployed for use in real-world applications.
The automated tools for digital systems are design, simulation, and implementation and testing of digital systems typically consists of different stages. Each of the stages will serve a specific purpose and the creation of the validation of the system. And before you can even start implementing automated tools, you must first identify and understand the requirements that will be for that digital or that specific digital system. This will involve gathering specifications, functional requirements from stakeholders, and constraints. This will also involve defining the input and the output behaviors on the system, like determining the performance and the criteria of any specific standards or the regulations that are to be followed. The simulation of automated tools where there will be some functional simulation that will verify the correctness of the digital system behavior will ensure that the simulation tool will simulate the response on the system to a different scenarios or inputs. After using the tools and verifying the system and ensuring that it meets the specific requirements and behavior that are expected under all conditions, the fault simulation will play a crucial role in automated tools. So pretty much just seeing where all the errors and cracks you will see on the system. And then after that, just continuing testing and debugging and just making sure that the automated tool will end up working on a reliable platform. Automated tools increase the efficiency and a certain consistency when it comes to the system, making it efficient and also a money saver. In other words, making it a little bit more affordable when running a digital system.
In conclusion, we feel that our presentation offers a comprehensive overview of automated tools, digital programmable devices, and the IVE process dividing digital systems design in our modern world. We emphasize the critical role these elements play in accelerating the design process, improving productivity, and ensuring the functionality, reliability, and performance of any and all digital systems in various applications and devices. Thank you for joining us in this exploration of the digital frontier. Let's embark on this journey together as we unravel the intricacies of the modern electrical design.